Hello everybody, this is the second online lecture for Math 127 Elementary Cryptography at Christopher Newport University. We have gone online because of the COVID-19 pandemic, and hopefully these are teaching you cryptography even while you're not sitting enthralled in my classroom. We are going to finish the lecture More Modular Arithmetic. The slides are available on Scholar, and I recommend that you have a copy with you to make notes on. We will be starting at approximately slide 63 if you want to jump ahead to that point. Also, I want to point out that I'm going to be demonstrating some numerical facts using Mathematica in this lecture. I will probably use commands that look unfamiliar to you. Don't worry about them. I am using those just for expediency. These are things that I would be writing on the whiteboard in a more conventional lecture, and I'm just doing them quickly using Mathematica to make things go fast. Okay, so where we're at right now, we're looking at moving to a larger modulus n instead of using something as small as 26. This has forced certain questions on us that we've been avoiding, namely, we know that something is going to be invertible mod n provided it's relatively prime, i.e. its greatest common divisor is 1. But when we've been working mod 26, it's easy to check almost just by looking at something whether or not it's relatively prime to 26. When n is a much larger number, that's not possible. All right, so we've seen already how to compute the GCD using the Euclidean algorithm, which is basically repeated division with remainder. And then when it is relatively prime, we can find A inverse by using a Euclidean table. This leaves us with one last question to answer. Namely, if I have some large value n, I know how to figure out whether something is invertible. I know how to find out its inverse, but are there a large number of invertible elements? If there aren't very many invertible elements, mod n isn't going to be a good value. So we need to know, given a number n, how many values between 1 and n are relatively prime. Okay, so one extreme is if I take an even number, then anything that is also even and less than that number is also going to be non-invertible. It will be divisible by 2 in both cases. So we never want to take an even number because at least half the values will be non-invertible. They'll have a common factor of 2. Okay, now when you're looking at these kinds of questions in math, we always start by looking at prime values. Primes form the building blocks of all numbers, and so if we can figure it out for primes, that's always a good start. So that's what we're going to do. We're going to look at first few primes. We'll start with some small ones, namely 5, 7, 11, and 13, and work out how many relatively prime numbers there are. All right, to do this, we will go over to Mathematica. All right, so let's simply start with 5. Okay, so we're going to look at the values 1 through 5, and we want to know which ones are relatively prime to 5. Okay, a slightly easier question. Can we figure out which ones aren't relatively prime to 5? Okay, so which numbers between 1 and 5 have a common factor with 5? Well, 5 is prime. So its only factors are 1 in itself, which means that 5 is not relatively prime to 5, but all of these values are. So in particular, 1 through 4 have to be relatively prime to 5. All right. If we do the same thing with 7, we can ask the same question and we get the same kind of answer. If I look at the numbers 1 through 7 and I simply remove those which aren't relatively prime, so something that has a factor in common with 7, well, the only thing that has a factor common with 7 is 7. So 1 through 6 have to be relatively prime. And so I get most of the numbers, or all of the numbers, strictly less than 7 to be relatively prime to 7. All right, well, this pattern continues. If I take 11, which is prime. Again, any number strictly less than 11 has to be relatively prime, so I get 1 through 10. And likewise, if I do 13, anything strictly less than 13 will be relatively prime, namely 1 through 12. Okay, that's good. Now, if we look at primes, as I said, they're good. If P is a prime, and I want to know whether a number A is relatively prime to P, well, they won't be relatively prime if they share a common factor. But the only thing that factors P other than 1 is P itself. So as long as P doesn't divide A, they must be relatively prime. Okay, this is part of why we like prime numbers. We can take any value less than it, and we know that it is automatically relatively prime. The other thing is when we take values larger than it, again, unless it's an actual multiple of the prime, we know that it's going to be relatively prime as well. Okay, so as it says, we like prime numbers, and in particular, we like really large prime numbers. Now, as a side note, we will never run out of prime numbers. Okay, we've known this since ancient Greek times. Euclid himself gave a proof that there are infinitely many primes, and every math major learns it. It's a classic. So we can find arbitrarily large prime numbers, which is important for us because as computers get more and more powerful, we need larger and larger prime numbers. And we are guaranteed an inexhaustible supply. As a side note, we can also go arbitrarily large distances between them. So if you want a range of 100 numbers where none of them are prime, you can do that. You can do that for any kind of gap that you want. We won't make specific use of that in this class, but you need to know these things for cultural knowledge, if nothing else. Okay, so back to the question. Given n, we want to know those values a, how many there are such that the GCD of a and n is 1. This question has been around for a while. It was answered a while ago as well. And it was answered by the Swiss mathematician Leonhard Euler. And by the way, that is Euler, not Euler. He developed a function which is now known as the Euler Phi function or the Euler Phi function, or sometimes called the totient function. It's denoted with the Greek letter phi, hence the name Euler Phi. And phi of n is simply the number of integers less than n and relatively prime to n. Now, what this means, we've already seen one example. All right, we've looked at primes p, and as I said, anything that's strictly less than p is going to be relatively prime to p. So that means there are p numbers between 1 and p minus 1 of them will be relatively prime. Okay, that tells us what the Euler phi of a prime number is for any prime number. Well, once you have it for primes, the next thing to look at are prime powers. Okay, so you take a prime number and you raise it to some power successively larger and see if you can find a pattern. All right, so we're going to look at the first few primes and their first few powers and see what we notice. Okay, so we're going to use Mathematica to do this a little. All right, so let's start with 2 squared. All right, so we're looking at the numbers 1 through 4, and we want to know which numbers are relatively prime to 4. Okay, again, it's easier to see which numbers aren't and remove them. Okay, well, if I want something that isn't relatively prime to 4, it has to have a factor in common with 4. Well, factors of 4 are 2 and 4. So the numbers that aren't relatively prime, are 2 and 4, which leaves 1 and 3 as the relatively prime values. All right, so we get, as I said, 1 and 3. Now, at the beginning of this video lecture, I mentioned I would be using commands in Mathematica that would look very unfamiliar. This is probably the first of those. Don't sweat it. It is not something that you will ever need. I am just using it so it will rapidly give me the numbers 1 and 3 rather than having to type them out individually. Okay, so now let's look at 2 cubed, or otherwise known as 8. All right, so I'm going to take the numbers 1 through 8, and I'm going to do the same thing. I'm going to remove those that aren't relatively prime. Okay, well, to not be relatively prime to 8, well, the factors of 8 are 2, 4, and 8, so it has to be divisible by one of those two numbers. Now, the thing that makes it a little easier, if it's divisible by 4 or 8, then it's also divisible by 2. So all I need to do is remove those things that are divisible by 2, or in other words, keep the odd numbers, and those will be the ones that are relatively prime. Okay, and indeed, if I remove those, I'm left with 1, 3, 5, and 7, namely the odd numbers between 1 and 8, and those are the ones that are going to be relatively prime. All right, we'll push one more power. All right, if I go up to 16, and again, I want to remove those that aren't relatively prime. Okay, well, to not be relatively prime to 16, it has to have a factor in common with 16. So the non-trivial factors 2, 4, 8, and 16. But again, if it's divisible by any of 16, 8, or 4, it's divisible by 2. So, once again, when I'm working with the prime power 2 to the 4th, anything that's divisible by the prime 2 has to be removed, and all the rest will be relatively prime. And sure enough, when I do that, I'm left with precisely the odd values between 1 and 16. Okay, so let's summarize what we've seen so far. And again, this is one of those commands, it's just for expediency to print what I need. Okay, so here we see the successive powers of 2. 2, 2 squared, 2 cubed, 2 to the 4th. Here we see the number of values that were relatively prime to 2, 2 to the squared, 2 cubed, or 2 to the 4th. And if you look at it, a pattern immediately emerges. The number that were relatively prime is precisely half those of the number that we were looking at. Now that pattern is not going to continue quite so nicely, and as we will see with other primes, but it is indicative of a larger pattern. Okay, so let's look at 3 now. Okay, so let's just quickly get our ranges of values. Okay, so 3 is prime, and so if we look at the number of values that are relatively prime to 3, we see that we should get 2, namely 1 and 2. All right, now let's look at 3 squared or 9, and again, let's remove those that aren't relatively prime from consideration. All right, so if we want something that isn't relatively prime to 9, then it has to have a factor common with 9. Divisors of 9, non-trivial ones, are 3 and 9. So it would have to be anything that is a multiple of either 3 or 9. On the other hand, if it's divisible by 9, it's divisible by 3. So we should remove any value that is divisible by 3, namely the multiples of 3, 3, 6, and 9. So when we remove those multiples of 3, we're left with 1, 2, 4, 6, 7, and 8. All right, now, if you notice, there are 6 values. All right, let's do the same thing for 3 cubed. Okay, well, to be, again, relatively prime to 27, it has to have factor in common with 27, which basically is 3 and 9 and 27. All right, but if it's divisible by any of 3, 9, or 27, it's divisible by 3. So we need to remove all the multiples of 3. So we'll remove 3, 6, 9, 12, 15, 18, 21, 24, and 27. All right, when we do that, we're left with these values. Okay, and you can count them up if you want, but we get 18. All right, so we got 6 when we were looking at 3 squared. We got 18 when we were looking at 3 cubed. Let's see what happens with 3 to the 4th. Okay, well again, I can go through. I have to look at the common factors of 81, but 81 is 3 to the 4th. Every factor of 81 is 3 to some power. So if it's going to have a common factor, it has to be a multiple of 3. So I remove every conceivable multiple of 3, and I'm left with those which are relatively prime. And if I want to know how many there are 54. All right, so to summarize, again, if we look at 3 here, the power of 3 in the first column, and then the number of values relatively prime in the second column. So it was for 3, there were 2, for 9, there were 6, for 27, there were 18, for 81, there were 54. All right, now, that may not seem like an obvious pattern, but there is one if you look. If I take 9 minus 3, I get 6. All right, that's useful. If I take 27 and I subtract 9, I get 18. And if I take 81 and subtract 27, I get 54. Okay, so now let's do it for 5. I swear this will be the last one. Okay, so now we'll take 1 to 5 squared, namely 25, and again, we want to remove those which aren't relatively prime so we can get a count. Well, again, it has to have a factor in common with 25, but the only factors of 25 are 5. So any multiple of 5 has to be removed, namely 5, 10, 15, 20, and 25. All right, which leaves us with those values there, and just for fun, we see that there are 20 of them. All right, 20 happens to be 25 minus 5. All right, 5 cubed. All right, well, now it's the numbers 1 to 125. And again, I need to remove those things that share a factor with 125. But the only prime factors of 125 are 5s. So 5 squared, and 5 cubed. But if it's divisible by any of 5 squared or 5 cubed, it's divisible by 5. So I just have to remove all of the multiples of 5. All right, and that's what I do. Now, that's what I do when I put the correct power in. All right, well, how many is that? It's 100. And 100 is 125 minus 25. Because there are 25 multiples of 5 between 1 and 125. Okay, well, now if we do it for 5 to the 4th, which is 625, well, again, it's every multiple of 5 between 1 and 625 that has to be removed. How many are there? Well, that's a good question. Once we remove them and we count, we get 500. And 500 is 625 minus 125. So we actually start to see a pattern here. If we're looking at prime powers, if I want to know the number of values less than or equal to p to the n that are relatively prime to p to the n, I start with all of the numbers from 1 to p to the n, and then I have to subtract all the multiples of p. There are p to the n minus 1 of them every time. Okay, notice that this is coherent with what we saw with phi of p. Phi of p is p minus 1. 1 is p to the 0. So p to the first minus p to the 0 gives me p minus 1. All right, so that tells me how to find the Euler phi of a prime and tells me how to find the Euler phi of a prime power. But what if I'm dealing with something that's not a prime power? Okay, if I'm dealing with 10, 15, 21, if we were in class, I would probably make you guys explore this on your own, but this is not the format for that. So we're going to use a very powerful fact about the Euler phi. It's what's called a multiplicative function. If I have two numbers that have no common factors other than 1, then the Euler phi of their product is the product of the Euler phis. This tells us how to compute every Euler phi we need. If I have something that isn't prime or prime powers, I break it down into prime powers. So I take n and I factor it into my primes. Different primes will be relatively prime, and so I can work out each one of these individually and then multiply them all together, and that tells me the value of the Euler phi. Okay, so that's a lot of formulas and so forth. I promise it's not that complicated. Let's look at some examples, namely phi of 26, phi of 100, 101, 180, and 324. All right, again, I'm going to just type this in Mathematica for convenience. All right, so phi of 26. So I go through my process. Is it prime? No. Is it the power of a prime? No. So now I'm going to factor it. So if I look at 26, 26 is 2 times 13. All right, those are relatively prime to each other, and each is a prime in and of itself. So that means that the Euler phi of 26 is going to be the Euler phi of 2 times the Euler phi of 13. 2 and 13 are prime, so their Euler phis are 1 less. So the Euler phi of 2 is 1, and the Euler phi of 13 is 12, and 12 is the Euler phi of 26. This is exactly what we've seen. Things are relatively prime to 26 if they are odd. Okay, so there are 13 numbers that are odd, less than 26, and they're not 13. So that removes 1, and we're left with 12. All right. Now, Mathematica has the Euler phi native. Its command is get this, Euler phi, and we can verify our answer like so. All right. Now let's do phi of 100. Now, again, 100 is not prime, and it's not a prime power, so I'm going to have to start factoring it. Now, the important thing is to factor it into things that are relatively prime. I could factor 100, oops, wrong format. 100 is 10 times 10. But I can't take the Euler phi of 10 and multiply it by the Euler phi of 10. Those aren't relatively prime. Okay, 10 and 10 clearly share a common factor, namely, well, 10. All right, so while I could factor it that way, that's not enough. Okay, but I could keep factoring it. So 10 is 2 times 5. So it's 2 times 5 all squared. which is 2 squared times 5 squared. Okay, well now 2 and 5 are relatively prime, 2 squared and 5 squared are relatively prime. So my Euler phi of 10 is the Euler phi of 2 squared times the Euler phi of 5 squared. And, whoops, wrong key. And both of those I know how to compute. Those are Euler phis of prime powers. The Euler phi of 2 squared is 2 squared, 4, minus 2 to the first. And then the Euler phi of 5 squared is 5 squared minus 5 to the first. So 25 minus 5. So the Euler phi is 3 times 20, otherwise known as our good friend 60. And if we want to verify that, we find out I'm wrong. Where did I make my mistake? Oh, sorry, that shouldn't be 4 minus 1, that should be 4 minus, yeah, that should be 4 minus 2, sorry. All right, so if I do that, I get 2 times 20, which is 40. I had a feeling 60 didn't look right. Okay, sorry for that. So that should be 4 minus 2. 2 squared minus 2 to the first. Okay, moving on. Euler phi of 101. 101 is prime. So it is 1 less. The Euler phi of 180. Okay, well again, I'm going to have to start factoring it. I know that 180, that's 3 times 60. Those are not relatively prime. That's not going to work. So we need to keep going. So that's 3 times 60. 60 is what? 3 times 20. And 20 is 4 times 5. Okay, so this is 3 squared times 2 squared times 5. All right, so the Euler phi of 100, whoops. Euler phi of 180 is going to be the Euler phi of 3 squared times the Euler phi of 2 squared sorry, keep hitting my page up, page down buttons, times the Euler phi of 5. All right, and again, each one of those I can work out. So the Euler phi of 3 squared is 3 squared minus 3. So this is going to be 9 minus 6, or sorry, 9 minus 3, which is 6. All right. Then the Euler phi of 2 squared, which is 4 minus 2. And then the Euler phi of 5, which is 1 less than 5. All right. And I get 6 times 2 times 4. Okay, which is 24, which is 48. And let's double check it. Sure enough, 48. Okay, so now I would recommend pause the video for a few moments and see if you can figure out the Euler phi of 324. Okay, so we're going to figure out the Euler phi of 324. I know the recording sort of cut off at the last moment, very abruptly. Somebody was coming in. All right, well, I take 324 and I factor it. All right, so 324 is 2 squared times 3 to the 4th. So my Euler Phi of 324 is the Euler Phi of 2 squared and the Euler Phi of 3 to the 4th. All right, 2 squared, the Euler Phi of 2 squared is going to be 2 squared minus 2 to the 1st, so 4 minus 2. And then the Euler Phi of 81 is going to be 81, which is 3 to the 4th, minus 3 cubed, which is 27. All right, and I am not going to try and do that in my head. If I work that out, it's 108. And as I said, we can just double check for 108. All right. So the Euler Phi function we're going to see is going to play a critical role in RSA encryption when we get there, and the exponential cipher in particular. So it's going to be very important. Now, there are, as I mentioned, the steps seem a little daunting at first, but it's just a matter of being very methodical. You start with n, you factor it into primes, and then you compute the Euler Phi of each prime power individually. It's important that everything be relatively prime when you factor it, and that you put all the powers of the prime together when you're doing the Euler Phi, because otherwise things will be off. All right, that is the end of this lecture. We will continue on to what's called the exponential cipher in the next lesson, I believe, though I reserve the right to change my mind when I'm looking at things. All right, good luck.